All right, students, I wish I had time to do more examples in class. That's true for every chapter. And I thought I'd just do a little supplemental lecture. And the classroom's busy, so I thought I'd do it from my desktop here. But when we kind of rushed to the end of Chapter 13, I thought it might be good to do some examples. So let me start with number 2 from the book, and then I'll still do video solutions as you have more challenges here. But I'll just pull up the hard copy here of the book. It says, frost damage to most plants occurs at temperatures of 28 degrees Fahrenheit or lower. What is the temperature on the Kelvin scale? All right, so one equation we had is the temperature in Fahrenheit is equal to 180 over 100 times the temperature on the Celsius scale plus 32. And so I like to think of this as you take the temperature on the Celsius, which is a measurement above ice water. Since there's more divisions in the Fahrenheit scale than the Celsius, you multiply it by this ratio of 180 to 100. And then it's offset by 32. And so I'll use this in the first step. And then the second step is to say the temperature on the Kelvin scale is the temperature on the Celsius plus 273. So I will say that they gave us this, 28. And then from there, we could solve for the temperature on the Celsius scale. So if I bring the 32 over, that becomes a negative 4. If I reduce this to 9 over 5, temperature Celsius, bring this over, and it's negative 20, divide by 9, and that's the temperature on the Celsius scale. So grabbing a calculator, that would be negative 20 divided by 9, which gives me about a negative 2.2 degrees Celsius. And it kind of makes sense because if you remember me in the lecture, I said that the temperature on the Fahrenheit scale for every 2 of these is about 1 on the Celsius. So I would say at 28, we are about 4 degrees below ice water. And then this 4 degrees might become 2 degrees, okay, on the Celsius scale. So my guess would be we should be about 2 below ice water. And on the Celsius scale, ice water is 0. So we should be about negative 2, and we're a little more than that. Actually, we should be a little more than 2, and we are. So that looks good. So then over here, I would say then on the Kelvin scale is the negative 2.2 plus the 273, which is about a 71 there or something. So 273. And that rounds to 271. So 271 Kelvin would be the temperature. Yay! Okay, so again, hopefully that could be useful. Let's try the other category we were working with. This is our thermal expansion. It says the height of the Washington Monument is measured to be 170 meters on a day when the temperature is 35 degrees Celsius. What will be the height on the day when the temperature drops? Okay, so keep that in mind. It's a drop in temperature. So this drop in temperature would mean it's going to decrease in size. So it's going to be smaller than 170. Although the monument is actually made out of limestone, go ahead and assume that it is a thermal coefficient of expansion is the same as marble. So if you know a little bit about geology, you know that limestone and marble are very close. They're a calcium carbonate. Limestone is a sedimentary rock. And then if it gets under pressure and heat, it gets a metamorphosis process and turns into marble. So they're really kind of one and the same, although one is a sedimentary rock and one is a metamorphic rock. So I think we're okay to use the coefficient of limestone and marble and probably dolomite and what are some other closely related, alabaster. And so your rocks that are basically seashells left over. So I think all of those we can get away with the same expansion coefficient. At least that's what they tell us to do. So I'm going to use this to say here is our equation for the change of something. The alpha is the material itself. Let me look that up. Let's see if I got enough room. But here we have a monument. Let's see, the Washington Monument, 170 meters tall. And the change in temperature, I think, is what they want to really emphasize, that it's a negative 45 degrees Celsius. So on a hot, looks like a hot summer day in Washington, D.C., it might be 35 degrees Celsius, and then 6 months later on a cold winter day, cold winter night even, it's a negative 10 degrees Celsius. So that's a drop of 45. So we've got negative 45. Now, the other thing I need to do is to look up these expansion coefficients, and it looks like it's on this page here. And so I can start here with my material, and it looks like down here they got marble. And so, as it said, I'll take that one. It looks like it's 2.5 times 10 to the minus 6 per each degree. So I'm going to put 2.5 times 10 to the minus 6 per degree Celsius, which is great because I'm going to be left now with meters. Okay, so 2.5 times 10 to the negative 6 times 170 times and I'll do the negative 45, will be a decrease, negative, of 0.019 meters. So about 19 centimeters. So let me take that original height. I turned the page. I think, didn't we say the original was 170? Yeah, 170 meters. Oh, yeah, it's right here. 170 meters. So 170 meters minus, and then, of course, to three significant figures, it's not even going to play a role. But let's say they meant 170.00 meters. And then we'll take off the 19 centimeters. So at least we have something to go by. And so, wait, yeah, 19 centimeters. Sorry. Yeah, I'm still saying that wrong. It's 19 millimeters. It's 1.9 centimeters. That's what I meant to say here. All right, so it's smaller by, this much. This is probably about 2 centimeters right there. Okay, so it will now be 169.9, and let me just call it 81. See that 19 over here. So it's 19 centimeters shorter. So, unless we really have it weighed accurate down into the centimeter range, we're significant figures, we're not going to see much of a difference there. All right, hopefully that will be helpful as you try to do the homework. Another good example is number 22, I think. Let's get that one. I think this gets the ideal gas. Yeah, so here it says the pressure gauge in your car tires read 2.5 times 10 to the 5 pascals at a temperature when it is 35 degrees Celsius. When you drive it into the ferry boat of Alaska, what is their gauge pressure later when the temperature drops to negative 40 degrees Celsius? All right, so this is kind of what I was saying in the lecture, that I'm going to use PV equals to nRT. I guess we could also say PV equals to Boltzmann's constant times NT. Either way doesn't really matter. If you put the variables on one side, that would equal R. or if you put the variables on one side, that would equal Boltzmann's constant. But if you refer to all of these as the initial conditions, then that same ratio of parameters has to equal R, and I'll call that the final condition. And you can do the same thing here. And so what you're really saying here is the initial pressure times the initial volume divided by the initial number of molecules times the initial temperature must then equal the final pressure, the final volume, the final number of molecules, and the final temperature. On the other hand, we could just kind of solve for different parameters using this. But I kind of like this statement. It allows me then to pay little to no attention what the value of R actually is. And so whether I set them equal to R or Boltzmann's constant, in other words, whether I'm using the number of atoms themselves or the number of moles, it doesn't matter. So I'll just do this one with the number of moles, but I think what they're trying to imply in this problem is that the number of moles don't change. There's a certain number that is in the car tire, and unless you open the valve, the number of molecules has to remain the same. They're not going to come in or out of that. All we've done is change the temperature. I think also this is trying to argue that the tires don't really, change their volume. Tires don't really inflate. They're kind of a hard rubber. They may look more elongated and squishy if they're flat, but they just bulge on the side. So you end up having roughly the same volume here. So I think they want us to say that the initial pressure over the initial temperature must be the same as the final pressure over the final temperature. And so for this particular one, the temperature dropped from 35 degrees Celsius and then really cold, I guess that's why we're in Alaska here, negative 40 degrees Celsius. So that huge drop here is corresponding to a huge drop in pressure. Now, the other thing to be careful about, and why I thought this would make a good example, is that this equation from the ideal gas law is talking about temperature on the Kelvin scale and pressure as absolute. And this problem doesn't give either of those. And so we could be in trouble here. So in other words, when it says the gauge pressure is 2.50 times 10 to the 5 pascals, we need to add to that the atmospheric pressure to get the total pressure. And keeping the same number of significant figures then, I would say that the absolute pressure, starting here, is 3.51 times 10 to the 5 pascals. And likewise, the temperature on the Kelvin scale is the 35 plus the 273. So 5 and 3 make an 8. 3 and a 7 make a 1. And so we're looking 308. Does that make sense? Let's see, 27 would make 3, and then 35. Yeah, okay. So we are at 308 Kelvin pascals. All right, but besides being the equation for the ideal gas law, I wanted you to see as you put them in, I've got to do the absolutes for each of them. The absolute temperature goes with the absolute pressure. That's how this was derived and worked out. So when they start giving you gauge pressure and temperature in Celsius, you got to convert that. Okay, so we're looking now for the final pressure in the tire, and actually gauge pressure, because if you read that question, it says, what is their gauge pressure later? So this is going to give me absolute pressure. Now let me take the 273, and to get the final temperature, because they said it's negative 40, let me put temperature in the Celsius plus 273. So this is going to cool down to 233, giving me a final absolute pressure, so I'm still not at a gauge pressure, but it would be 233 over the 308. So that's the 75% of the original absolute pressure, making 2.65 times 10 to the 1, 2, 3, 4, 5 pascals. And so now to make it a gauge pressure, let me subtract off 1 atmosphere. And I can drop that because it's sig figs, but this would be a 4, this would be a 6, and this would be a 1. And so now the gauge is going to read 1.64 in hundreds of kilopascals. And that's pretty common for a gauge. Those of you who were in person and did the lab in person, you saw that. We used units, a number, we wrote down our numbers, and they were in hundreds of kilopascals. That's 10 to the 5th, hundreds of kilopascals. So this looks like it really was cut in half, at least as far as gauge pressure. No, sorry, that's absolute. Where's gauge pressure? 2.5. No, that's not half. So it was reading 2.5 on the dial. Now it's reading about 1.6. Okay, so again, hope that kind of helps along with your understanding. Let's see, the next one I thought would be useful to you is to see somebody work out number 37. Okay, so 37, where is 37? I think this is also under the ideal gas law because these are just harder. What is the gauge pressure in a 25.0 degrees Celsius car tire containing 3.6 moles of gas in a 30-liter volume? Now, in that case, they're not really doing a before and an after, so I'm just going to go PV equals to nRT and see if they've given me enough information to solve for what they want. And again, that question is, what is the gauge pressure? So I think I'm after pressure, so I'll just put P. They gave me a volume, and here I got a judgment call to make. They gave me the volume in liters, so maybe I'll put 30 liters. They give me the number of moles, 3.60 moles. So, by the way, that would tell me I don't want to use this form where I use Boltzmann's constant and the number of atoms. Now, I could, because I could, once I know the number of moles, I could convert that into the number of atoms. So I'm not saying you can't do it that way. I'm just saying when you are doing it with the R, which they call the ideal gas constant, it's already in moles. So that might be a reason to say, let's not do that one and let's do this one. Here's the interesting thing, R, and let's talk about that for just a second. I'll leave it as an R, but I'm trying to find this, and I know R, except it's the units that got to match up. So let's talk. Maybe I should put moles here. So here's R. And then, of course, I need the temperature, and so this said the temperature was 25 degrees Celsius, and so this is my way of reminding you that the temperature needs to be on the Kelvin scale. So this is really a 298 Kelvin. Now, if you remember from the lecture, R, I gave you 2 values, and your book actually gives you a third value. The first value I gave you was 8.31, and if you do it in the base units, maybe instead of writing it as a joule, it might be better to write it as a Pascal times a cubic meter. So it seems appropriate to use this R of 8.31 if my pressure is in pascals and my volume is in cubic meters. Okay, well, I don't have it in cubic meters, although I could convert it, so that's not out of the question. The other constant, or the same constant but different values, the 0.0821, was when it is in units of atmospheric pressure and volume in liters, Kelvin and mole. Now, maybe that seems like the more appropriate R for this problem because I do have volume in liters. But of course, if I do that, then I will get the pressure in pascals. And that's okay. I just really need to know that and recognize it because they just ask what will be the gauge pressure. Let's see, containing, what will be the gauge pressure? And they don't really say whether I have to do the pressure in pascals or in atmospheres. So I'm going to take advantage of this one right here and say here's pressure, and so times 30 liters and 3.60 moles times this R, which is 0.0821 atmosphere times a liter, Kelvin over a mole. And then the temperature, as we just said, is 298 Kelvin. See, that way Kelvin will cancel off, mole will cancel off, liters will cancel off, and the only thing I will be left with is atmospheres. So if I take 3.6 times 0.0821 times 298. Okay, so that's this side of the equation. Now remember there's a 30 over here, so I'll divide by 30. And so this should give me a pressure of 2.1, well, let me call it 36. And liters, 30, yeah, they said 30.0, so 3 there, 3 there, 3 there, 3 there. Okay, so I'll go 1 extra here in my calculation because now I need to subtract off the atmospheric pressure to get gauge pressure, and the definition is, 1 atmosphere for the atmosphere. So we're looking at a pressure on the machine of somewhere around 2. See, the absolute pressure is 3, subtract 1, and a gauge pressure is really, really close to 2. Okay. So hopefully that adds some extra insights. And let's see, the last one on my list was number 39. And 39, I kind of rushed you guys there at the end in that kinetic theory model here, but it says some incandescent light bulbs are filled with an argon gas. So they have a gas, not a solid or a liquid. What is the RMS for argon atoms near this filament, assuming that their temperature is around 2500 Kelvin? So if you remember from the lecture, and without proof, we said the kinetic energy is related to the temperature, and it's related by these factors, the mass of it and the Boltzmann's constant here. And we can rearrange this, and we did in class. We could subtract off the 1/2, and we can write the speed squared averaged then would be 3 times Boltzmann's constant over mass times the temperature. And so if you take the square root of that, so 3 times Boltzmann's constant times temperature over the mass, what you're going to get is the square root of the average of the squares. And that's why we call it RMS. The RMS. Think of this as kind of like an operator where you would say kind of like sine of 30 degrees. So you got 30 degrees, and the thing you're going to do is take the sine. And if you had something that looked like the log of the sine of 30 degrees, you would say, okay, I'm going to start with 30 degrees, and first I'm going to take the log, and then after that, the sine, and then after that I'm going to take the log. Okay, so it would look, I guess, something like this. You would say, I'm going to take the log of 1/2, which I think I should write as log of 2 to the -1. So the negative can pull down, and then it's the log of 2, and I think the log of 2 is a 0.3, log of 2. You see that one a lot. Yeah, 301, and I should memorize it. Now you can even see here log of the sine of 30. And so there's the -301. Anyways, that's what this is saying here is if you have something, so be velocity, you first want to square it. Then you would want to take its average, so you'd add up all those and divide by the number. And you might say at that point you have the average of the squares, okay. And so now you take its square root, and that's kind of like getting back to the average, but it's not. It's technically the square root of the average of the squares. It would be like taking the numbers 2, 3, and 4. Their average is 3. You can add them together, 5, 9, and divide by 3, 3. So the average is a 3. But the RMS is going to be a hair higher than that, because you would take all those numbers and square them. So it would be a 4 and a 9 and a 16 when you square them. You would add them together and divide by 3, so that's the average. Then you take the square root, and so you end up with 3.11. And so what is the square root of the average of the squares is not quite the same as the average. Conceptually, you might think of it as being one and the same. But we're not interested in their averages because we're interested in their average kinetic energy, which is the average of their squares. And so this is the idea. The average of the squares, which as you saw from the numbers I just did, the average of the squares was 9.66. Whereas if I just take these numbers, or take the average and square it, I get 9. So the average of the squares, the RMS, is not the same as the average squared. And that's worth mentioning in this problem because, I don't know, conceptually you kind of think about them as the same. But mathematically, they're not the same. And that's worth pointing out. And I ran out of time to really do that. But I will point out, your author does this with a nice graph. And he looks at this and, I guess he doesn't have average. He has most probable. But he says, if you were to plot the number of atoms, so probability, at different temperatures, you would get only a few that are going slow and only a few that are going fast. And most of them are in this range of about 400. In fact, there's a lot of them right here at a number a little bit under 400. So he calls that the most probable state. That's true. Now, if you were to average all these, you'd get right about here. But if you were to take their RMS, that is, you would take the square root of the average of their squares, it gets a little higher because these numbers that are squared play a big role. For example, 5 squared is 25. That's a much, much bigger increase over, say, 1 squared. So if you had numbers like 1, 2, 3, 4, and 5, the lowest one, 1 squared, is a 1, but the highest one, 5 squared, is 25. There's a big spread between them, and it makes the average of the squares higher than just the average. And I guess he just did that for probability. But you will always get this. You'll get the most probable is a little bit on the low side of the average, and then the RMS will be a little on the high side of the average. And so it's important to point out, because like I said, conceptually we often talk about the average of the squares, that is the RMS, as being the same as the average. And that's really not what we want. We really want the average of the squares because we want to know the average kinetic energy. That's our goal, is to know the average kinetic energy, and that takes the average of the squares because kinetic energy has velocity squared. All right, well, I hope I didn't dictate too much lecture there, because now that maybe you have a better understanding, let me go back to the question. Where is it? 39. It says here, what is the RMS of the argon gas, assuming the temperature is 2500? So I'm going to take this formula down here and say, okay, the RMS will be, and so I have a 3. Then I have Boltzmann's constant. Then I have times the temperature, and let me just check. Since this has to do with motion, this should be in meters per second, and this should be in joules and Kelvin, and that should be in Kelvin. And so sure enough, they say 2500 Kelvin, which is kind of typical for one of these incandescent argon gas bulbs here. Now, the other thing is divide by the mass of that molecule. That's the argon. I don't know if I remember seeing a periodic table. In our current textbook. So, for better or worse, I'm going to grab a different textbook. Maybe I should just use the one that I'm showing you guys. Oh, no, I haven't shown you that. I made some lectures for next semester. Okay. But here's a nice periodic table. And argon is one of the noble gases, so I'll jump over here to argon. And they said argon has a mass of, and so this is the atomic mass number. Let me just call it 39.95. So 39.95. And these are called atomic mass units, where an atomic mass unit is a small amount of mass. Kind of makes it nice to work with atomic mass units instead of some kilograms. But in terms of kilograms, it's 1.67 times 10 to the negative 27 kilograms. And depending on which way you round, it could be 1.66. Let's see what this book has to say. Front cover. Where is atomic mass unit? Up at the top. Yeah, 1.66 times 10 to the minus 27. So 1.66 times 10 to the negative 27 kilograms. And also, I guess I'm showing my age here. They used to call them AMUs for atomic mass units, but the new symbol, and a couple decades old, is just the mu. Okay, so that'll let me do a calculation here. So it's 3 times Boltzmann's constants times the 2,500 and divided by the mass, which is the 39.95. That's also divided by 1.66 times 10 to the negative 27. And now, final step, which is taking the square root. So this would be about 1,200, and I'll just call it 50 for significant figures. So 1,250 meters per second is the RMS speed. So there are ones going faster, there are ones going slower, and as we said, the average is actually a little slower, and the most probables are a little slower. But this would be the value to use if you ever wanted to figure out some kind of connection to the temperature, because temperature is related to the average kinetic energy. And kinetic energy is related to the square. So we want the square of the, I didn't say that well. So we want to know the average of the squares, not the square of the average. Yeah. All right, so I hope this little supplemental was useful. Thought a few extra examples that if we had a half hour extra time in class, I would have loved to have shown you, but I'll just tack them on here, and you can study them on the lecture video. All right, take care.